So we have functions and the notation that go around that. So the definition of a function is actually a fairly straightforward thing, and there's one absolutely key aspect to a function that distinguishes it from any other equation or any other mathematical statement that you want to make. A function is just a rule that connects an input to an output, and the thing that's distinguishing about a function is that you get exactly one output for every input. So there's no gray area in here. You can't have x equals plus or minus 3. Or the function equal plus or minus 3. That's not a function. A function gives you one value for every input. So it's a little bit like saying, what is your height? And your height may change with time, but today you are a particular height, and so your height is a function of right now and who you are. So you get one value out of that. And so think of a function as you put something in to a definition, that definition gives you a result out of that, and you get exactly one result. So you can use function in plain English just by saying, the output is a function of the input. So what's the temperature today? Well, the temperature today is a function of the time of day and the location that you're at. Okay, things like that. We're going to be dealing primarily with functions of one variable. So we'll have one input value, one output value. Okay, so did somebody have a question?
Can we finish writing?
Oh, yeah.
No, I mean the last.
Yeah, I'm going back.
Oh, okay.
How's that? Okay, shall we go on? Okay, so let's do a couple questions here. I've alluded to this in my opening comments about is height a function of age? And it is. How about the other way around? Is age a function of height?
No.
Think about that, right? You can be many ages at the same height. How about, is price a function of an item? You generally expect so, right? You don't get up to a checkout counter and they say, this item is $1 or $1.50. I mean, there's usually a rule that will make it exactly one price. How about, is the item a function of the price?
No.
It's not, right? Because you can have many items that are priced with that have the same price, and so just by knowing its price doesn't tell you what item that is. And so if you get a letter grade, is your test grade a function of your score? So if you get a value, do you have a letter grade? You do. How about the other way around? So it's not true. Just because you have an A doesn't necessarily mean you have a 93 or a 97 or any of those scores. Okay, so we're going to look at a different kind of definition here, and we're going to talk about a one-to-one function. And so a one-to-one function is a function where there is there's exactly one value in the output of the function for every value that you put in. That's true with all functions. But then the reverse is also true, that the output values correspond to exactly one input value. So we refer to this as being one-to-one. So here's a couple questions. Is the weight of water a one-to-one function of the volume of water? So in other words, if I tell you I have a pound of water, can you tell me what volume of water that is? And vice versa, if I give you a volume of water, can you tell me its weight? And so it is, right? There's a direct correspondence. Now, of course, we can get really fussy about this and you say, well, you can change the temperature and things like that and the volume changes, but we're just doing an ordinary thought experiment here. That means that any given input has exactly one output and every given output has exactly one input. Okay, so if you have 8.5 pounds of water, you have 1 gallon of water, and vice versa. If you have 1 gallon of water, you have 8.5 pounds of water. Okay, and we've already talked about this a little bit. The weight of a person, a one-to-one function of the height. So for example, if you know the weight of a person, do you know their height? And if you know the height of a person, do you know their weight? That's not true at all, right? In fact, that changes certainly by the amount of body fat you have. So can you suggest a one-to-one function? I mean, I've given you a couple examples here. Think of something that in ordinary life would be a one-to-one function. Alex?
Each age corresponds to exactly how many months you've lived. So if you're like 1 year, you're also 12 months.
Yes. So there's an equivalence between the time in years versus time in months if you consider fractions and decimals and things of that sort. Yes. So you can say at 24 months you're exactly 2 years. Okay, that's a good example. Anybody else? So there's a feeling, I think, that a one-to-one function is a special function in the sense that it's perhaps easy to construct a function, something that, you know, once you know one property, you can determine the other. But to make it work both ways, you know, there has to be something special about it. Okay, so let's talk about the symbols that we're going to use for a function. And so if we say distance is a function of time, okay, so what's the output then in this phrase? It's distance, right? And so the input is time. So at a certain time, you're at a certain distance. So now one of the things that you'll discover about me is that I really value the definition of variables, and I also value you stating what the units are. So whenever you're doing something and you're inventing a model or you're writing some sort of math equation, where possible, write the definition, just like this. T is time in hours. And so we say d at t is the distance in miles at time t. So there again, I put the units in miles, put the fact that d at t is a function that tells me the distance. If you give me the time as an input, I'll give you the distance as an output. So we have a little bit of ambiguity in the notation here. Okay, so you can go along and you write a letter in front of some parentheses with another letter, another variable on the inside. And so if you just write d, open parentheses, t, close parentheses, do you mean d is a function of t, or do you mean d times t? And so it can be either way, right? And so here's where your definitions become very important. So when you're writing a model, it is helpful to write those two lines. D equals time in hours, d at t is distance in miles at time t, so you're not talking about the product, because this isn't anything of distance times time, this is distance as a function of time. And so there's no convenient way to be sure that you're talking about a function instead of a product unless you just write it down, that d at t is a function. Okay, so there's four ways that you can define a function, and we generally refer to functions in terms of algebraic expressions, but there's three other ways that we can do it. We can do it verbally. Okay, if I say that I'm 5 years older than my brother, that's a perfectly sound definition of a function, right? I tell you my age, you know my brother's age. And so most functions present themselves verbally or in some type of ordinary language. It's up to us to translate it into something that is a little bit more easily manipulated mathematically. But we also have tables that show a correspondence. You can have a number of things like the prices in a catalog, things of that sort can be in tables. We can also represent functions as graphs, and the advantage of graphs is that you have a nice visual impression of what happens just by a glance. So you can see, does the function increase with your input variable, like does distance increase with time? Is it steady? Are there wild changes, things of that sort? So graphs are beneficial, but they are also less precise in the fact that we have to read off very carefully what the numbers are. So we tend to reduce everything to algebraic expressions, which is the most friendly way to do it in terms of being able to do some mathematical manipulations. So just keep in mind that a function isn't necessarily the expression d at t equals t squared plus 5 or anything like that. That you do have functions that are represented in a variety of ways. So let's look at a table here, and we can kind of exercise our understanding of notation by reading this table. So let's say here you have age in years, and here you have a weight in pounds, and so you have to evaluate the function w at 10. Okay, so the function w at t is a function that describes weight. So what would w at 10 be? 70, right? We read it directly off the table. Now what about solving w at a, where a is an age, equals 125? That would be 15, right? So notice there's two subtle differences in the words that I'm using there. Evaluate means I'm taking an input and evaluating what the output is. Solving means I'm going to look for all the values of true of a, which makes this expression true. So a little change in the sense, but it essentially is the same meaning, where you want to connect the input and the output by your definition of the function. Okay, so let's look at a little different notation here and go to this quotient that we've seen before in the derivative presentation. So I'm going to say let a equals 10. So we're going to say 10 years. And when we talk about delta a, we're talking about differences in a, right? So we're talking about a2 minus a1 equals delta a. So we're talking about 5. So what does this mean when we say delta w over delta t? Well, if we look at a plus delta a, we're looking at a second value of the age. So if a is 10, delta a is 5, w at a plus delta a would be w at 15 then. And then w at a is 10, so that would be, we would read that as 70. So what do you suppose this means? So if I take a second point, subtract a first point value of the function, and divided it by the difference in our input, what does that look like? I'm sorry? It's a change in weight over a period of time is really the meaning there. And so what would this mean in ordinary language then? I'm sorry?
Is that the derivative?
It is the derivative in a sense. It's not the derivative at a point, but we're talking, the derivative is the slope of a line at one point. This is the slope between 2 points, right? So This is the average change then. The derivative talks about the rate of change at a particular time. When we're talking about these deltas, where delta A is 5 years, this is a substantial number of years, we're looking at that first W of A plus delta A is W at 15. So that means that's 125 pounds. So if we say 125 pounds minus W at A is 70, so we have 125 minus 70 divided by 5. What that means is that we've increased in age or increased in weight over a certain period of time. So this is the average weight change over 5 years.
Okay, so in the top
Oops.
part, we're subtracting a function from another function, and then the bottom is just a number and a change in age. Is that
Yeah, the top is the value of the function, is the output of the function. And
how do we
the,
know their functions, though?
what's that?
How do we know their functions? Like, I thought that was like kind of.
Well, I said it, I didn't write above there, W at A is a function that describes the
So
weight.
we just like kind of say this is a function, like literally just.
I'm telling you, W at A is a function, yes. And probably I should have written here, W at A is a function, you know, A is the age, W at A is the weight at a certain age.
I'm confused about the whole delta thing.
Yeah, okay, well, let me write this on the board. And so if we look at just a regular slope of a line, we have this y2 minus y1 over x2 minus x1. So let me translate our graph here into, or that table into a graph. So if I'm at 10 years, I'm looking at 70 pounds. Okay, so there's 1 point on my table. Now a little bit further along, at 15 years, I'm at 125 pounds. So if I look at the line that connects these two, and I want this slope, what I have is 125 minus 70 over 15 minus 10. So this here, if I put this in words, this is the change in weight. And then this is divided by 15 minus 10, which is the change in time. And so I can abbreviate this change. Remember, I said earlier that the delta we can use as a symbol for change. So this is the change in weight. This is the change in time. And so this is going to be the second weight minus the first weight. This is going to be the second time minus the first time. And so if I express this as a function, this is going to be W at A plus delta A. So this is our starting point, and we're adding a change in time, minus our starting point A. And then this, of course, is just going to be, the second time is A plus delta T. So it's 10 plus 5 years, minus the starting point, which is 5 years. And so the A minus A cancels that out, and we just get delta T. And so that's how that's constructed.
So this is just this, slope formula, right?
It is. This is, we're making this now something that we're going to call the quotient, the difference quotient, because we're looking at the difference in the value of a function divided by the input values of that function. So the notation here is going to become increasingly more important as we talk about derivatives.
Do we have to use the whole delta thing, or can we just find the slope?
No?
Because it's confusing. I don't get it.
Well, this is the part that we're stepping into calculus here. Okay, so when we're talking about functions with graphs, the independent variable is on the horizontal axis, and the dependent variable is on the vertical axis. Generally, when we make a y, we say, or we make a graph, we say the x-axis is on the horizontal one, the y-axis is on the vertical, and the y would be the function's value, x would be the function's input. So if I have three different graphs here, you can see that, and I haven't labeled them as x and f at x or anything like that. I'm just, by convention, I'm saying that the input value is going to be the horizontal and the vertical is the output value. We call that the independent and dependent variable because the independent variable is the one that you choose. I can say, what does x equal? And if I get an x, then that tells me what the y is. So we say y depends on x. Another way of saying that is, what's the value of x? Well, choose it. What's the value of y? Well, it depends on x. Okay, so we don't necessarily choose y in the sense that it's independent. We choose our input value and it gives us an output value. So here we have three graphs, and now which one is a function and which one is not? The first two are functions, and the third one is not. Why isn't the third one a function? Very good. Somebody said vertical line test. That's exactly what we're getting to. It does not have exactly one y output. So if we take a look at where x equals 0 of that first one, you see that it can either be at the top of the circle or at the bottom of the circle. So we have two values that correspond to a single input. Now that's a perfectly good relationship. It's just not a function. Okay, so which ones are one-to-one? Just the first one, right? And so somebody had said it already, the vertical line test tells us if we have a function, and then the horizontal line test tells us if it's one-to-one. So you can see in the first one, there's no vertical line that we can make that will cross that line in two places, and there's no horizontal line that we can draw that crosses the graph in two places. But the second one, even though it is a function, there's only one, any vertical line touches the graph at only one spot. When we make a horizontal line, we can easily draw one that touches it in 1, 2, or 3 spots. And of course, the last one, when you don't have a function, it can't be a one-to-one function, right? It has to be, that's kind of the base definition, is that a one-to-one function is, after all, has to be a function. Okay, so the most, I guess, familiar way to define a function is through algebraic expressions. And so we often come up with equations in two variables, and we can sometimes convert those equations into functions. Okay, that's a little bit like saying, well, in this example where we have 2n plus 6p equals 12, that in itself isn't necessarily a function. That's a relationship that there's certain pairs of n and p that make that true. But if we rearrange this thing to say, okay, I'm going to be choosing my n and I want to figure out what my p is, we're declaring n to be the independent variable and p is the dependent variable then. And so depending on the model that you have, this is a decision that you make. You have this relationship. There may be a perfectly good reason why you want to define it the other way around, but we choose in this case to make n as the independent variable. And so p at n, or p of n, depending on what you want to say, is the way we would notate that function. And the way we would get to the function would be to solve basically for p. And then instead of p being a variable, we can make p a function. All right, so in the very first thing, it looks like n and p are variables. As I go through and I solve for p, so I have the steps that I took was I subtracted 2n from both sides, then I divided both sides by 6, and then I reduced it, so p equals 6 minus n over 3. I can declare then that p is now a function, and we can notate it as such. Okay, So what I'd like you to do here is write this down, and I will back up to that last slide. I know there's a couple people that were still writing, but first write this problem. I want to find a function a of b out of this equation. So I have 3a plus 4ab plus 2b equals 7. So there's an equation that has some sort of relationship between a and b. I want to make it so if I give you a b, you give me the a. That's the function I'm looking for. If everybody has that written down, I'll go back to the last slide just to let you complete your notes if there's a few people that want to round that out. Oops. Okay, so did you get something? It's a little trickier than that linear equation I had earlier, right? Because of that multiplication between the a and the b. Okay, let's start out and looking at the solution here. Okay, so in the first step, what I did was, since I'm trying to find a as the function, okay, that's the output that I want, I remove everything that doesn't involve the a to the right side of the equation. All right, so I have 3a plus 4ab equals 7 minus 2b. Now what I can do is I can factor out that a, and so I get 3 plus 4b in parentheses times a equals 7 minus 2b. And then I'm going to divide both sides by the 3 plus 4a, and I get a equals 7 minus 2b over 3 plus 4b. And so I can declare a is now a function of b, where a at b equals that 7 minus 2b over 3 plus 4b. So you're going to be doing this a little bit, trying to solve for these things. When we get into things like implicit differentiation, we're going to be doing this a lot, actually, by trying to isolate a particular variable. And when you have products, it's sometimes tricky. So the general strategy is, see if you can get all the terms that involve what you're trying to isolate on one side of the equation and get everything else onto the other side, and then you can factor out that, that particular variable like you do here. You can kind of drive yourself crazy by trying to first maybe put 4ab on one side of the equation, but then you have that a straggling on the other side or so. So just keep in mind that this is probably the best strategy for solving an equation like this is get every term that involves your variable on one side, everything else on the other, and then factor out what you're looking for, and then you have a ratio of things. Okay, any questions on that example?
Like, once I do it, how do I know for sure that it's a valid function?
Well, that's a good question, that you can solve for A. At this point, every B that you put in, you'll get exactly one value, right? And so we're going to see a couple functions that we'll attempt to solve that aren't valid functions. Something will happen. What will generally happen is that we'll have essentially two equations that come out of this solution. So let's look at the next one, which is an example of, I think, what you're asking. Not every equation can be made into a function. Okay, so let's look at this one. This is at a circle. Okay, we already know from that example before, that a circle, well, I'll just let all this play out here. We already know that the circle fails to be a function and that the circle fails to be a one-to-one function. Okay, so this x squared plus y squared equals 1 is just a generic equation of a circle. So if we were to solve for y, let's say I want, y as a function of x in this, what I would do is isolate the y squared equals 1 minus x squared, and then I would take the square root. But remember, when you're taking the square root of a square, you actually get a plus or minus in there. And so to really solve this, we have y equals plus or minus the square root of 1 minus x squared. This cannot be a function because we get two values. If I put in a 0 in that x, for x, I get plus or minus the square root of 1, which is plus or minus 1. So on that circle, you have the point 0, 1, and 0, negative 1. And so that means that, of course, it's not a function because for one value of x, I have two values of y. And so when we're trying to translate these things, we get equations, and it happens a lot with roots, and it happens in a few other circumstances, where we would get more than one value. In general, when we have things like the one before, where you just had products and there's no higher power, it's just things added and multiplied to each other, you'll get a function out of that. You may not get a one-to-one function, but you'll probably get a function. When you have higher degrees, like a squared or so, when you're taking the square root, you're going to end up with a plus or minus. And so those are generally the deal breakers that say, oh, this is no longer a function because I have two values that come out of this solution. So when we have this expression, when you finally solve for y, you have to say, is this a function? And it violates the definition of a function, so you don't have it. So it's very well possible that you can solve for y. Now, of course, not every case is an easy solution where you can isolate the variable that you're looking for, and that's an entirely different set of problems. If you have polynomials in a higher degree, sometimes you can't always solve for them. But in this case, we can solve for it, we just don't get a function.